Welcome to the SAMPE Q&A session for inspection and repair, and thank you all for joining. I'd like to make you all aware that the session will be recorded and posted on the SAMPE website for on-demand viewing. If you have any questions throughout the duration of the session, please type them into the Q&A window found on the control panel of your Zoom meeting window. My name is Richard Leducer. I am a postdoctoral researcher at Montana Tech in Butte, Montana. And mainly my research focuses on process design and optimization, specifically in sort of the hemp fiber world. So I'm going to introduce the panelists now. So our first panelist is Sagar Doshi from the Center for Composite Materials at the University of Delaware. Sagar is a final year PhD student at the Center for Composite Materials. His research focuses on the processing and characterization of nanomaterial-based hierarchical composites with applications in sensors. Sagar has been actively involved with SAMPE as a student chapter president in the past, bridge competition participant, and now an officer in the Baltimore, Washington chapter and Young Professionals Committee. He was also awarded the PhD scholarship by the American Society of Composites and the dissertation fellowship at the University of Delaware. His talk in the virtual session was characterizing the effect of transverse strain on carbon nanotube-based sensing skins for structural health monitoring. Our second panelist is Harry Frederick from Louisiana State University. Harry Frederick is a master's student in the Department of Mechanical and Industrial Engineering at Louisiana State University. He is working on damage detection strategies for welded thermoplastic composite joints under the supervision of Dr. Genevieve Pilardi, and plans to graduate in fall 2020. He previously attained his bachelor's degree in chemical engineering at LSU in 2015 and worked at Jacobs Engineering Group. Harry's talk for the virtual session was on multifunctional films for fusion bonding and structural health monitoring of thermoplastic composite joints. Technically, our third and fourth speaker is Chris Sacco from University of South Carolina. Chris is a graduate researcher at the University of South Carolina's McNair Center for Aerospace Innovation. Chris graduated with a BS in Physics and Applied Mathematics from Presbyterian College in 2017 before earning a Master's of Science in Aerospace Engineering in 2019. He is currently pursuing his PhD in Mechanical Engineering. His previous research includes inspection in the automated fiber placement process and machine learning applications to composite materials. Chris is a member of the USC Next Future Factories research team and is exploring areas related to predictive maintenance, decision-making under uncertainty, and hardware acceleration of control methodologies. Chris's first talk was on a quantitative evaluation of AFP steered courses through inspection. And his second talk for the virtual series was on NDE inspection of AFP manufactured cylinders using an intelligent segmentation algorithm. Our fifth speaker is Sandeep Chava. Sandeep Chava is currently a third-year PhD student at Embry-Riddle Aeronautical University, working in the area of structures and materials. His research focuses on composites and nanocomposites in aerospace and aviation. He is a member of the Advanced Mechanics and Materials Group at Embry-Riddle and also an active member of AIAA and ASQ. His title for the virtual series was Evolution of Composite Defects During Manufacturing, Wrinkles, and Delamination. Our sixth speaker is Ariel Lusty from Montana State University. Ariel received her BA in Physics from the College of St. Benedict in 2016. She is currently a doctoral candidate in mechanical engineering at Montana State University in the Composites Research Group. Her research involves comparing surface preparation techniques for wind turbine field repairs. And the title of her virtual series presentation was a comparison of surface preparation techniques for wind turbine field repairs. Our seventh speaker is Giles Dillingham from BTG Labs, LLC. Giles has worked in the areas of materials, surfaces, interfaces, and adhesive bonding since receiving his PhD in material science in 1987. Recent work by Dr. Dillingham and BTG Labs is helping pave the way to certifiable adhesively bonded primary aircraft structures. Dr. Dillingham has over 40 publications and patents in the areas of surface treatments, surface energetics, and adhesion. He is proud to have been elected a Robert A. Patrick Fellow of the Adhesion Society. Dr. Dillingham's virtual series presentation was on the remediation of contaminated bond surfaces and contaminant mixtures.
Hey, Richard. So we do have the other two, speaker 8 and 9 are here, so we can go ahead and introduce them too. Perfect.
Our A speaker is Muthu Ram Prabhu, and I'm going to mess up his Elenchezhian. Did I get there close, Muthu? Okay, and he's at the University of Texas at Arlington. Muthu is a doctoral degree-seeking candidate in the Department of Mechanical and Aerospace Engineering at the University of Texas at Arlington. He works as a graduate research assistant in the Institute of Predictive Performance Methodologies at UTA Research Institute. His research interests are in the field of composite materials, structures, adhesive bonds, manufacturing of composites, dielectric characterization, strength and life prediction of composites, machine learning, and deep learning. The title of his virtual series presentation was Performance Enhancement and Prediction of Composite Materials with Embedded Electrospun Piezoelectric Sensors. And our speaker 9, our last speaker, is Sergio Rodriguez from California Polytechnic State University, San Luis Obispo. Sergio is an aerospace engineer who recently graduated from Cal Poly and now pursuing his master's in the same field. He is looking forward to working in the aerospace industry, specifically improving and working on structures. His virtual series presentation was Structural Health Monitoring of Composites from Carbon Nanotube Coated E-Glass Fibers. So now, as I've introduced the panelists, we'll begin the Q&A session. My first question is for Sagar. Sagar, in your presentation, you talked about lower and higher concentrations of your carbon nanotubes for your sensing skins. What were those lower and higher concentrations, and were they the same for every method that you tested?
So a quick highlight. So we had 3 different processing techniques. One was calendering or 3-roll mill, where the nanotubes were mixed in the resin. Then there was dip coating, where the nanotubes were deposited on the non-woven aramid fabric. And then there was electrophoretic deposition, where again the nanotubes were deposited on the aramid fabric. And the high concentration was about 0.5% by weight of carbon nanotubes in the entire composite sensor. And that was for both the 3-roll milling and the dip coating technique. And the lower weight concentration was about 0.2% by weight. And for the electrophoretic deposition technique, because we have a lot more control over how much nanotubes we are depositing by varying the voltage and the field strength and the time of deposition, we had a higher weight percent of carbon nanotubes. So the specimens that were called higher concentration had 2 weight percent, and the lower concentration was about 1 weight percent. So basically, in summary, again, like we are comparing the sensitivity of all these different processing techniques on the sensing response, and we're showing that while concentration has a significant influence on the sensitivity, but the microstructure of how the nanotubes are integrated within the composite sensor also plays a very important role.
Thank you, Sagar. The next question is for Harry. Harry, for your thermoelectric behavior, you claim a linear dependence. What is the adjusted R-squared for your linear regression?
Right, so for the, let me see if I can pull up the relevant thing. I'll share the relevant graph that I was talking about. It was this figure here. And for this weight fraction of nanotube polypropylene, the R-squared was 0.9039, so fairly linear, or a fairly good fit for a linear fit. We also studied 2 other weight fractions of nanotubes and polypropylene, 20% and 25%. The 20% had a R-squared linear fit of 0.89, and the 25 weight percent had the lowest R-squared of 0.83. As far as why the R-squared of the 25 weight percent nanotube loading has such a low R squared. That's something that we had to look into in the future.
Okay, thank you, Harry. Chris, the next couple questions will be for you. For your quantitative evaluation presentation, you talk about success rate, but what was the success rate, and did the system catch every defect?
No, so the system did not catch every defect, and that really wasn't the intent that we were going for. So we were rolling at about 85% rate, and it's a little bit fuzzy when you get into semantic segmentation because it's not just the raw pixel score. You're also talking about, how well are those pixels grouped together, things like that. So it was about 85% accurate, but then because we had developed all these additional tools, including a user interface and the ability to very quickly correct and change boundaries of defects, things like that. We had a secondary algorithm whose name was Matt, who came back and went through our data set and was actually able to make the corrections where they were needed to. So the actual end results were completely fully validated by humans and were able to come back and do it. The important part for us, though, was not necessarily the overall accuracy. It was about having proper data representation and then being able to utilize that data representation to be able to say, what exactly, can we put a quantitative value on the quality of this particular course? Can we effectively measure how many defects we have during layup, things like that, and getting a good representation for that? So the rough answers, we were hitting about 85%. We came back and fixed the errors that we would have through some software that we had developed previously. But more importantly, it was about data representation, being able to utilize that data properly, and then taking that data that we've collected and using it to analyze what the quality of our overall layup would be.
Okay, so the next question is related to that segmentation. Then in your presentation, you mentioned artifacting in the algorithm. And so are the artifacts merely an effect of generating the diagram, or could they be unbounded defects?
Yeah, I believe you're referencing the Voronoi with that question. Yeah, okay. So they are strictly residuals from the Voronoi. They're just unbounded edges that are coming off our pseudo center line. They're just productions that you get whenever you run a Voronoi over something that's not a perfectly rigid, perfectly structured shape. So it's just a result of the computation itself. It might be interesting to include those points later on. So we've done a little bit of work since to talk about how maybe we could even utilize that information to come back and improve our centerline fit. So for right now, we want to get rid of those, but in future work, there's a chance we could wind up actually incorporating those, even though they're not the exact representation that we're looking for the center line.
Okay, the next question will be for Sandeep. Sandeep, can you elaborate more on the benefits of the novel in situ characterization approach versus the ex situ?
The research on composites, mainly the evaluation of defects in composites, has been studied very well since 1800s. Fairly, when the use of composites is around 1 to 5% in the airframe weight, but now it increased to 50 to 60% of the airframe weight. And even some manufacturing companies like Honda Jet are making their complete fuselage out of composites. So the importance of composites in aircraft is continuously increasing. With that increase, there is also increase in getting a high performance or decreasing the defect factors when we are manufacturing these composites. So with that, there is high necessity for an in situ approach to detect these damages or delaminations that are happening in the composite in the early stage during the cure, rather than comparing, let's say, using an ex situ approach like an X-ray, where you can do X-ray only after the complete part is completely manufactured. So for that, we came up with an approach using autoclave to do in situ using digital image correlation. And that approach can capture damages such as delamination or wrinkles during the manufacturing of the composite part itself. So that's one of the primary reasons why we have used an in situ approach rather than ex situ approach. This saves both time and capital for manufacturing companies, so that if they find any defects, they can stop the processing before completing the whole part.
Okay. The next question is for Ariel. Ariel, are the solvent wipe tests that you use a standardized test, or did you follow a method from literature?
So solvent wipe tests are not standardized. The solvent wipe methods that were used in Dorworth's book, Essentials of Advanced Composite Fabrication and Repair, were used. And the book recommended sanding, then wiping with a solvent, and then wiping again with a dry cloth. And then I think from what I read, the same method was reiterated in Dillingham's paper in this conference, remediation of contaminated bomb surfaces, contaminant mixtures. And then there was another paper on developments in testing adhesive joints, which was written by Bruce Duncan, in which Duncan mentions that the single lap shear test can be used for qualitative and comparative measurements. So for example, checking the effectiveness of different surface preparations or ranking strengths of different adhesive systems. And so there's an ASTM standard for lap shear tests, but and then solvent wiping is a form of surface preparation. So I essentially synthesized the solvent wipe methods from Dorworth's book with Duncan's suggestion that lap shear tests can be used to compare surface preparation methods to conduct the solvent wipe test that I used for my paper.
Okay, thank you. Giles, how do you envision this discovery to be utilized, incorporated in manual processes that still exist in manufacturing and repair?
So, some more here. A whole lot of our work is focused on how do we bring quantitative process control into operations like adhesive bonding of composites and metals. Bond performance depends on control of a few molecular layers of the composition, just a few molecular layers of that bond surface. And really, a whole lot of our work is trying to introduce quantitative controls into these processes, because currently they're typically, manufacturers depend on process control, not measurement, to try to control these processes. And we use a lot of contact angle methods. We use portable contact angle goniometers. We manufacture some very nice ones for this purpose. They work quite well. A lot of that work was discussed in the paper. There are potential other methods. Portable ones are kind of in short supply. We typically use portable wetting, portable contact angle goniometer methods. So.
Okay. The next question is for Muthu. Muthu, how do you explain the impedance contradiction results to that of the information from literature that you obtained?
Yeah, so I'm just sharing my screen right here. So from the literature, what we have so far observed, this plot, the yellow color curve shows the permittivity curve. So when for permittivity, what we have so far observed is that the permittivity increases and then has a steady decrease, and it has a final decrease when it ends to failure. And what we expect from the physical relationship for impedance, that we want it to decrease in the beginning and then have a general increase and have a rapid increase when it approaches failure. But what we observed from my experiments was that we first had a small increase and then decrease and then increase. What we thought was that we have used a unidirectional laminate in which all the layups are in 0-degree direction. So when we saw a mechanical curve as well, it has a sudden death, sudden failure. So we assume that will be one of the main reasons. And the literature data is all for the true along the length of the material. The impedance data was collected along the length of the material. But in our experiments, the impedance data was collected through the thickness of the material. So we assume these factors will make these variations.
Okay. And then the last of the first round of questions is for Sergio. Sergio, how would you improve your manufacturing methods, your dip coating and those things?
So one of the things we first tried to do was try to sonicate the solution where we had the epoxy and the carbon nanotube powder in there. That proved to be inefficient because as you sonicated it, you would add too much energy, and this would cause smoking and it to heat up too fast, which would create it, make it to where it would harden too fast, so you couldn't really coat your strands. So when that didn't work, we went into a breading method where we didn't pre-impregnate already the carbon and nanotubes into the epoxy. So one of the things we would want to improve with the converged solution of a breading method, we would want to be able to quantify how much carbon nanotubes per mass we can incorporate on each strand. This proves to be difficult because you don't really know how well it's going to stick to the carbon nanotubes unless you already pre-prescribe a certain amount of carbon nanotubes that you're going to sprinkle on and make sure every single particle is on there. But that's how I would improve our methods, is by quantifying how much of those breading material is actually attached to the e-glass sensor.
Okay. Next question is for Sagar. Sagar, what compressive load do you think would create permanent damage to your sensor?
So again, giving a little bit more background. So these sensors that we're making are piezo-resistive sensors. So essentially, whenever there's some sort of a mechanical deformation, the electrical resistance is going to change, right? And the change in resistance is due to like two main mechanisms. Like one is because of the change in the tunneling gap between the nanotubes, and in certain cases that at higher strains, because of cracks, it can lead to the damage of the conductive electrical networks, and that can also cause a change in resistance. So far that from our experiments, what we have noticed is that whenever you're in the elastic range, whether you're in tension or in compression, as long as the strain is in the elastic range, you do not see a permanent change in resistance. So if you're doing cyclic loading within the elastic range, then you would see the resistance would come back to its original or the baseline value. And then whenever you go beyond the elastic range and you start seeing cracks in the network, that's when you see like a permanent damage to the sensor or a permanent change in the electrical resistance.
Okay, thank you. Harry, for your resistive heating experiments, why was the highest temperature achieved in what appears to be very specific geometric points? You're muted, Harry.
There we go. Better. So I believe the question refers to this thermal.
Yes.
Yes. So that just has to do with the distribution of the nanotubes in the polymer film itself after being compression molded. You know, this one in particular has 25 weight percent of the nanotubes. This one, it just has to do with the how the network of nanotubes is arranged and how the electrons flow. So that's it's a processing result of the processing conditions, really.
So would you want them to be better distributed throughout your?
Yeah, and this one, it shows, you know, they are really would group up in these high temperature zones. So it just shows that they are not very well distributed in some of these samples.
Okay. Now on to Chris. Chris, what other fields could this be applied to? It is profile based, so could it spot things like pores in ceramics or inclusions in casting? You're also muted, Chris.
There we go. Yeah, it absolutely could. So basically anything where you have something that you're looking to identify that causes a disruption across a surface is, so essentially as long as it's not colored, you can actually get a profile off of it. Yes, you could theoretically apply this to. And we've had ideas about trying to take this over towards some different metal processing or some different metal or metallurgical processes, and trying to do some stuff with that. We've also had some ideas about how to do it, even with assembly robots or assembly operations for robots, kind of checking that they've got good contact between two different points before you lock in the assembly operation. So a lot of stuff like that, yeah. And the cool part about profiling is that you can start to do some interesting stuff by reconstructing surface geometry. There's all sorts of additional features you can pull off of it. So yeah, it's very highly applicable to a number of different potential processes in manufacturing and inspection.
The application that I was thinking of specifically was 3D printing, metal powder 3D printing. So,
Yep.
And then for your segmentation algorithm, how did you verify the results? Visual observation, you mentioned operators looked at it. So how did you verify the results?
Yeah, it was two factors. So we could actually bring up the scan images themselves and see. So the software that I mentioned before that we had used to do corrections, it's the exact same software that we're running this system on as well. So it's very easy just to pull up a scan and verify that it is where it needs to be. And then obviously we walked over to the part and we went and found the defects themselves to do rework and repair. So it's a little mixture of both, basically. So we could verify that the algorithm was looking at the correct thing on the computer on the scan, and then we could make sure that Axis was pointing us to the proper location by actually walking over to the part and physically doing the repair.
Okay, thank you. Sandeep, how do you see the future influence of this project?
Right, so the influence of the project, we made a significant improvement for the research that I have published in SAMPE. So after SAMPE, we made a lot of improvement for the process in identifying the reason for manufacturing defects. And one of the primary reasons we found out was ply slippage or ply movement during the processing of composites. So we even published a journal, Journal of Manufacturing Science in detail about this identification. And we were recently awarded an NSF grant to further investigate this ply slippage at a ply level. So in SAMPE, we were mainly talking at the laminate level. So now we are concentrating on ply level to see what is the primary reason for the ply slippage. And the future goal is to come up with a plan to alter the cure cycle of the composite so that we can minimize this ply slippage, which in turn minimizes the manufacturing defects. So that's the future goal.
Okay, thank you. Ariel, which plasma treatment would you use if the results are similar? How would you use it? How would you use the plasma treatment in field?
So since the results were similar for contact angle testing, you could do further testing by applying plasma prior to adhesive bonding, and that could assist in determining which plasma treatment to use for a specific application. And then, so I sanded samples that were identical to the ones that I had solvent wiped, and then I shipped them to a company called Enercon in Wisconsin, and they did the blown ion and flame treatment, and then the samples were immediately contact angle tested. So if you look at the differences between blown ion treatment and flame treatment, so blown ion plasma treatment effectiveness is dependent on the distance that you are from the substrate. And so that indicates that maybe varied distances could result in different surface properties or surface energies across the surface. So blown ion treatment might be more effective for smaller repairs, but not so much larger repairs. And then flame treatment is less sensitive to distance. So it might be a more viable option for field repairs. But I don't really see either treatment being viable for rope access field repairs due to accessibility issues. So wind turbine blade technicians have to carry their repair materials with them in bags while they're suspended from the nacelle of a wind turbine. And both blown ion and plain surface treatment options, they take up about a cubic foot of space and have to be plugged in, and they don't really look particularly light. So I only see plasma treatment being viable in the field if a standing platform is used. And then even then you would need a generator to power the plasma machine. So for now, I only see the plasma treatment being used either on a platform or in a warehouse for repairs to wind turbine blades that aren't yet in the field.
Okay, it sounds like there's a innovation needed in that area. I just thought it would be interesting watching a guy with a plasma gun trying to repair a wind turbine blade. So, Giles, what are the next steps for your project for this topic?
So next steps are, and so again, what we're trying to do here is develop techniques that put quantitative process parameters onto bonding operations for either manufacturing or for repair. And so basically where we go from now, we extend the database to a larger, more materials, more contaminants, different types of contaminants. And really the next step is to promulgate this sort of information and this sort of approach and bring it to the attention of people that are currently doing bonded repairs and bonded manufacturing. A whole lot of it comes down to when you study bonding for a while, you quickly gain an appreciation for the sensitivity of the performance of a bonded structure to seemingly small process excursions, right? And you walk into a manufacturing operation and you'll see one operator is doing a really good job of cleaning surfaces prior to bonding, changing their cloths frequently, confirming the solvent is clean, et cetera. And then you watch another operator the next shift, something like that, and this person may be reusing the same wiper cloth 20 times in a row, may drop it on the floor, pick it up and wipe a bond surface with it again, right? These are processes that depend on, again, a couple molecular layers on the surface, and that they're being performed by people that are not trained to have a sensitivity for the delicate nature of these bond surfaces. And really the next step, there are many next steps, but it's simply trying to inculcate in the industry an appreciation for the fact that if you're going to bond a structure and you want that structure to have a known reliability, then you better pay attention to controlling all the parameters around that bond surface preparation that can affect that bond performance that people are simply not doing right now.
So a lot of training and highlighting what's important is sort of what you're suggesting.
Training, and it's also, again, putting in quantitative measurements, right? Ariel mentioned things like contact angle measurements. These are great ways in a manufacturing environment to get real-time feedback about what's the molecular state of that surface. Did I get a thumbprint on there? Is that solvent drum, did somebody clean greasy parts with their solvent and then pour it back in the drum, and now other people are using the solvent out of that drum to clean bond surfaces? We see that happen, right? You got to combine this appreciation, the sensitivity, with quantitative, objective measurements of the important characteristics of the bond surface.
Okay, thank you. Muthu, what is your interpretation of the random behavior of the PVDF samples in the impedance versus displacement graph?
So this is the PVDF of impedance, PVDF samples data, and the impedance is a displacement graph. For two samples, we observed the steady increase, decrease, and again an increase. But for other two samples, it was a different behavior. Like we had different thicknesses in the samples, as well as with 4 samples, we cannot conclude what was happening. Even for all the 3 experiments, we had only 4 samples data. And since this is unidirectional material and all were in 0 degrees, we had to use tabs, and we had bonding. We had to bond the tabs into specimens, and the specimens were also not clean. So we feel the surface contamination as the main reason, because the sensors were not cleaned properly and the samples were not cleaned properly with the bonds. So that might be one of the reasons. Hence, we are not sure of it exactly.
Okay, thank you. Sergio, you show probabilities and some statistics in your work. Did you look at the coefficient of variation for your experiments? And then did you look at doing some type of design of experiment?
So to answer the first question of the variance, what we did end up doing and concluding with was a box plot where we look at the probability of reproducing these same sensors, and to where we can also expect where this gauge factor can lie. This was like in the first stages of this work. So the range was fairly high, but in terms of additional statistics, we did not do more on that, no. What was the second question?
That was about design of experiments. Did you look into design of experiments of any kind?
Yeah, so we looked at various designs of experiments, and again, to reiterate what I had previously said, was that there was different processes to make these sensors. One was obviously have the solution sonicated. Others was to pre-impregnate the carbon nanotubes already, such as Bucky paper. We didn't get to that either. We also looked at breading, which there wasn't too much on that, so our work is really in the front stages of that technology, is the breading. But
Okay,
various designs of experience were looked at, yeah.
Yeah, so you had to get the manufacturing down before you can try to optimize it.
Right. So, and that goes back to like our statistics. Our statistics, there is some good data there, but in reality, we still have to improve on the manufacturing of the sensor before we can look at ways to improve it.
Yeah, that's what I got from your presentation. There's a lot of good stuff there. Just let's get the manufacturing.
Needs to be refined.
Yep. Okay. Thank you. That was the last of the prepared questions. Now I get to throw you all some curveball sort of questions. So as usual, we'll start with Sagar. What would you say was one of the most surprising, interesting discoveries with your research?
I would say the most interesting part was like, so even in our lab and just otherwise now we're using more and more nanotube based sensors, carbon nanotube or graphene based sensors for a variety of different applications, from strain sensing and others, right? And then calibration has been a real challenge, specifically as we move more towards applications in the industry. And even in our lab group, we're now starting to put sensors on the field. Like currently, we have some sensors on a bridge in Wilmington, Delaware, where we are sensing fatigue cracks. And we have a couple of sensors on a bridge in Portland, Oregon. And we're also working with a couple of oil and gas companies to put these sensors on their pipelines. And we realize that calibration is one of the major challenges going forward, and that's why we decided to study the influence of transfer strain on the sensing response. So like in summary, like the most interesting part was that typically we kind of characterize or get the gauge factor by performing a test in the lab, and we realize that that sort of characterization or calibration is kind of dependent on what substrate material we were using. And in this case, now when we did more extensive tests using a biaxial testing machine, we realized that for the kind of sensors that we are making, the Poisson's ratio of the material plays a significant part in what gauge factor we are calculating. And therefore, we now propose a slightly modified way to, calculate the gauge factor, which would then make the calibration material independent and hopefully give us better results in the field. So.
Okay, and that was also what I found most interesting from your work was the Poisson ratio effect on gauge factor.
Yeah, after you get the results, it kind of seems intuitive now, but like till then, when we're not considering the gauge factor and the influence of Poisson's ratio, and then it turns out to be a pretty important thing. So.
Yep, I agree completely. So, Harry, how do you see the future influence of this project?
Well, I think that this has a good, it shows good promise in the future of just quick spot welding, especially. I mean, I know that the ultrasonic welding has been shown that there is promise in longer continuous bonding, but being able to have a piezo resistive polymer film in between at the interface has a lot of promise in monitoring fatigue, cracks, and even in situ repair.
Okay. I also agree with that. So, Chris, what are the next steps for? We'll do it for both of your topics. What are the next steps?
Yeah, so there's so for the idea of getting quantitative descriptions of what your course quality is, or what your layup quality is for AFP, this is something that you don't really see a whole lot of. So having this down on paper, having a actual definite methodology to get this done opens up a lot of different avenues. So the first one that we've already started exploring, and hopefully we'll start to see some results that we can get out on this pretty soon, is we have descriptions of course quality by length of course. We also have done tracking of, I think I hinted towards this at the end of the paper, we've also done tracking of layup speed, compression, heater voltage, and we also have done tracking of obviously curvature of steered courses. And so that means that we have a description, or we have a description of course quality, and we have all these additional parameters. We can start to build bridges across to those disparate data features, or the features of our data set. So we can start to build predictive models off of this. We can start to talk about what are our statistics that we can explore as far as this goes. And the really neat part about this is then we can start talking about, all right, using inspection data, using all this additional stuff, and doing process improvement. So actually being able to come back and with hard data say, all right, this is where we'd expect, let's say, the process window of our material to be. We're getting this set of defects here. We need to come back and adjust this part of our process. We need to run slower at this point, or we need to have a higher heater temperature at this point. There's all sorts of additional things with AFP process improvement that we haven't really been able to tear into now, that now we can start to approach a lot of those questions, which will be extremely interesting, I hope. And on the side of our intelligent segmentation algorithm that we're using for inspecting the cylinders, the really cool part where we can go with this, and once again, I think I talked about this a little bit during the presentation at the end of the paper, was augmented reality systems. So we're tackling the idea of cutting down on inspection time and reducing inspection load on your operator. Now we can talk about the secondary component of that, which is rework on your part, which is so it's a huge component of your actual manufacturing time is dedicated just to rework inspection. So we're trying to take on one part of that problem. Now we think with augmented reality systems, we can actually better inform how people are doing the rework. So we don't have to look at a computer screen, walk over to our part and say, that looks like about the right placement. We can actually have a mobile application on a cell phone or have a headset where you are able to hold that up to your part and it'll actually directly show you on the screen, these are the locations you need to walk up to do repair. And we think it will massively cut down on rework time for AFP.
That's a good next step for this. The augmented reality was, I guess it wasn't something I was expecting to see in these presentations. So it shows a a good future use of a lot of these technologies and sort of how we can use these technologies in place.
Yeah, and hopefully next year I'll be able to come back and give a presentation on that. So
awesome. Okay, Sandeep, what would you say was one of the most surprising, interesting discoveries with your research?
The interesting discovery is the ply slippage itself. Before having an in situ approach, we developed the in situ approach to see what's happening inside an autoclave. Usually autoclaves are pretty sealed and we cannot see what's happening until the complete process is finished. But now with this approach, we can see during the processing inside an autoclave, how the plies are moving at different temperatures, at different time during the cure. So that's an interesting way to come up with new approaches where we can alter these cure cycles to decrease the ply movement. So having that part, that's an interesting approach to see what's happening inside an autoclave. And that's where we got the research idea of investigating the ply movement or ply slippage in the processing. So having an autoclave with that capability is an advantage, but it helped us in our research.
Yeah, no, being able to visually see anything usually helps in drawing conclusions about what's happening. So, okay, on to Ariel. Thank you. Ariel, how do you see the future influence of this project?
Future influence of this project. So, so at this point, I've looked at the effects of the solvents on the surfaces, and then the next steps would be to look at particularly the methyl ethyl ketone effects on the vinyl ester surface, especially with that methyl methacrylate adhesive. But in the long term, a better understanding of solvent wiping and contamination on wind turbine field repair surface preparation will let us develop more defined procedures for wind turbine blade technicians, and then that would create more reliable repairs on wind turbine blades.
Okay, and I'll ask the same question of Giles, since you have similar topics.
Do me a favor and repeat the question, would you please?
How do you see the future influence of this project?
So, in some ways very similar to what Ariel's saying, right? Improved, and again, quantitatively controlled, quantifiable repair processes, as well as manufacturing processes, right? And part of what we're trying to do, we're trying to bring some little more basic chemistry into things like developing and evaluating repair processes. For example, rather than, in the work that we did, rather than simply accepting a solvent manufacturer's sales pitch that solvent XYZ is going to be great for removing these solvents, we did a few very simple chemistry experiments to pre-screen solvents to remove specific contaminants from the surface. We did some simple solubility measurements, and we did simple extraction measurements on contaminated surfaces using FTIR to find out which solvents actually remove these contaminants the best, right? So that was, we like to kind of think a little bit beyond, beyond the nose on our face and question some of these assumptions. And then we back that up with functional tests like contact angle measurements. Did this solvent really do a better job of cleaning that surface? And then does that actually translate into better performance of our bonded structure at the end of that? So, if the next step is getting the folks that are designing and implementing bonding processes and manufacturing repair to start thinking a little bit more critically about this stuff, we will have succeeded. That'll be good. And hey, I wanted to make a comment, Ariel, that there's one or two real nice handheld plasma units right now designed specifically for composite repair. There's an outfit out in California called Surfex that's making one. it's a pretty cool unit. We've done some evaluation of it, and literally it's something you could walk up to an airframe or maybe a wind generator blade, and you can plasma treat the surface with this handheld thing designed to walk out there in the field and use. So it'd be worth it for you to look that up. Although in our experience, typically manual sanding and solvent wiping processes can sometimes be hard to beat in terms of getting a good performing bond.
Good to know. I'll look into that. Thank you.
Okay, thank you, Giles. Muthu, what would you say was one of the most interesting, surprising discoveries with your research?
So when we tested the samples with the normal virgin samples and the samples with the nanofibers mat in them, the nanofibers mat samples gave higher mechanical strength, and it actually increased that was on average of all the several specimens. So that actually was surprising for us because we mainly carried out the experiments to perform the impedance study on the nanofibers mat, but using nanofiber mat aided both the PVDF and PVDF along with MWCNT samples. Both of them increased the breaking load of the material. So that was more surprising, and what we want to do further is to do more tests on this and fatigue test on this to see if actually changes the fatigue life of the sample as well.
Okay, and then for our final question, I'll ask Sergio, what are the next steps for your research?
So some of the next steps for our research is basically my master's thesis on and what it's on. Basically, what we're going to end up doing is, now that we kind of have a good process for manufacturing these sensors, is to actually do some testing on it. So what I'll be doing, and it kind of got impeded by this COVID thing, but what I started doing was I started putting these sensors specifically on a cantilever beam and vibrate it such that we can find the natural frequency of the structure theoretically and see if our sensors are sensitive enough to find those natural frequencies as well. So this can be implemented in terms of like delamination, as you're like, namely on an airplane. As you're going very, very fast, you get small vibrations, but as soon as you start fluttering, you want to be able to capture that and, you know, adjust the plane to a speed that, you know, no longer have flutter. So my main thesis will be on capturing the vibration, seeing if the sensor can indeed sense those delaminations if it happens to occur, or try to prevent damage to the aircraft as well. So vibrations testing.
Okay. With that, I see I don't have any questions in the queue, so I would like to thank all of you for participating in this session. I'd like to thank the SAMPE organizing committee for organizing this, so you all could get your research out there and people can watch it and see it and see how amazing it all is. So if you have any additional questions, feel free to fill out the form on the track landing page on the SAMPE North America website, and SAMPE will follow up. Please make sure to check out the content being released next week for the manufacturing technology track within the virtual series. Thank you.